Hello, dear fellows. I'm Frederik Cui, a researcher from TU Eindhoven, the Netherlands. It's been a great honor to be here to present our recent work. Today, I will talk about the fundamental and application aspects of adsorption thermal battery, especially those scenarios involving with low-grade heat uses. We will focus on utilizing some new solvent materials, metal organic frameworks. I will split the talk into three parts. I will firstly present some backgrounds about water absorption using these materials. I'll show how to evaluate the performance of a thermal battery based on a view of science of engineering. At the end, I'll speak about the implementation of the technology in a built environment. So, MOFs are hybrid solid porous materials. These materials can absorb different gases due to their novel molecular structure. They are composed of an organic linker and a metal cluster with infinite topologies. There have been more than 90,000 MOFs discovered or developed by the chemists today. Water absorption is a recent hot topic in the research community, and it seems to let us see the possible game-changing solutions to some grand thermal challenges. People realize that water can be directly linked to energy due to the large absorption enthalpy. As common sense, the energy released by absorbing some vapor can heat the same quantity of water from 0 degree to 100 degrees. So the process reveals the possibility to apply the new materials to all existing technology based on thermal energy storage and transport, including drying, heating and cooling, water producing, etc. As you can see, the materials are discovered less than 3 decades ago, and it is now a large branch in both fundamental chemistry and environmental science. Fortunately, after 20 years of efforts, several companies and establishments over the world can now mass produce some MOFs, which lays the foundation of our activities. I am one of those people who believes this field will contribute to shaping the future of our energy industry. So I engaged myself into this subject, and it is why I'm bringing this subject to the symposium at MIT, looking for potential large deployment of the technology in the near future. The principle of the adsorption machine is rather simple. We have a higher temperature source that inputs energy, and at a low temperature, we obtain a cooling effect, and at the mid-temperature, we obtain heating effect. All the process doesn't consume any electricity. The principle has been discovered by Michael Faraday almost 200 years ago. The key is flexibly using the principle with advanced working materials to develop novel thermodynamic cycles, new mechanisms, and new functions. We can build closed system for cooling with one evaporator and one condenser. We can build a semi-closed system for water producing with only one condenser. And we can build also open system for thermal storage with only the adsorption units. So here is some design to date for the use of thermal battery at small scale. Prototypes for 20 watts were demonstrated for temporal cooling scenarios. The system was much compact and stable than a PCM thermal battery system, despite its appearance. We can see the state of art of this particular research branch from the schema on the right. The largest application of the thermal battery is to use it for the built environment, especially with the increasing penetration of renewable energy. It is prioritized to find low cost and robust storage solutions, which allow us to reduce the energy fluctuation while maintaining the same piping and pumping equipment sites. The adsorption thermal battery is installed at the demand side. Thanks to the nature of high energy density, it is more applicable for intraday application than conventional system. In this way, the thermal battery achieves peak shaving and load shifting with reasonable cost to the end users. We fabricate a small proof of concept. We run lab tests and field tests. We characterize the performance of the MOF thermal battery. We use complex modeling tool in CFD to capture the phenomena and mechanism of heat and mass transport. In such an open system, we consider the porosity of adsorbents, the fraction of vapor flux, and the intermolecular and intramolecular diffusion external. However, the performance of an adsorption thermal battery has never been investigated carefully. In current system design, including what I've shown of the temporal cooling solution, we have the temperature profiles like on the left, which is enabled by the operation of constant temperature flow, very common in the engineering. Since the adsorption mechanism involves a complex heat and mass transport, the power output is not linear to the external flow rate, which in fact gives a variable heating and cooling performance. This is not acceptable for the market. It's difficult to measure and it's difficult to pricing. The researchers and engineers in the thermal and civil engineering disciplines just adopted an average value of the performance without further looking to a standardization of the performance of a thermal battery or any type of thermal batteries. This makes the state of research on thermal batteries striking far behind the electrochemical batteries. And now we are trying to bridge this gap. Here is a standard characterization method of electrochemical batteries. The C value here refers to how quickly the battery is discharged entirely. For instance, 2C means the battery of 1 kilowatt-hour is discharged in half an hour with a power of 2 kilowatts. And 0.5C means discharge in 2 hours. This higher, the higher the power density is, the less the usable energy density of the materials, and also the lower the energy density of the battery. So we use an analogical method to convert all the parameters of our adsorption thermal battery to that of an electrochemical battery standardized. Using the experimental and the modeling characterization techniques, we are able to find the real performance, the constant power output of the thermal battery and the various operation conditions. As you may see from the screen, the thermal battery, similar to an electrochemical battery, always hold a trade-off between the energy density and the power density. The higher power output we produce, the lower energy storage we can use in each cycle. This character is of vital role in the development of a thermal battery. It tells us we must find the optimization performance between installed energy capacity and the operational conditions. The trade-off is related to the material properties and the mechanical design, sizing properties as well. With the obtained energy power performance map now in real conditions, we can finally evaluate the true economic value of such a thermal battery system. We consider a representative household in the Netherlands that has already installed a heat pump system and now faces the question of whether adsorption thermal storage has additional value. Note that we use a heat pump to blow up a hot airflow at a higher temperature than normal heating needs to charge the thermal battery. The airflow with discrete temperature is still conducted to the house for heating use. Here is the profile of heating demand and energy consumption in a typical winter day. Absent of any thermal battery, the household will self-consume the energy, identical to the profile of heating demand, despite the fluctuation of electricity price in the spot market. We develop an intelligent control framework to implement the thermal battery in the building heating system. The total energy capacity can be discharged or charged by the heat pump in 4 hours with maximum power. The control aims to minimize the electricity consumption costs for operating the heat pump. In this framework, we have state variables for the state of charge of the thermal battery, space and heating demand determined by weather data and building available properties. We have control signals for day-ahead electricity prices. We have constraints from minimum and maximum power of the heat pump and the thermal battery. Now, we have the performance of the thermal battery. On the left, we can observe the operation of the battery during the day. The heat pump outputs also change accordingly, which lead to a lower consumption of electricity, as shown on the right hand. With the cost differences, we can easily calculate the maximum allowable LCOE of the thermal battery. With these models and validation, combining the physical mechanism and the optimal control, we can derive many figures of merits to describe the thermal battery performance with high precision. For instance, the loss in the switch between charge and discharge in average is acceptable. More energy has been produced because a thermal battery can harness latent heat from the air. Total energy electricity consumption has been saved by 15%. Both energy load and the price profile can be moved by a large part as the added value, etc. This thorough evaluation process is indispensable to develop and implement adsorption thermal battery in realistic conditions. And to largely deploy this technology in the near future, we must establish standards for the characterization of the performance in order to make more accurately estimation of the cost factors. And to summarize, we have demonstrated how to calculate the figure of merit of a thermal battery more accurately. And now we know that adsorption thermal battery is a promising storage technology to improve energy flexibility, providing high energy and power density. We have clarified that the figure of merits are comparable to an electrochemical battery. The trade-off between energy and power density were found, which were neglected in previous research in the areas of civil and thermal engineering. MOFs, thermal batteries, generated at a low temperature, can be integrated into various scenarios without additional heating equipment. It's suitable for high-shared renewables. Finally, MOF thermal battery can serve for both load shifting and demand shifting. The latter cannot be fulfilled by conventional thermal storage technologies to date. So this is the end of my topic. Thank you very much. I'll be very happy to take questions.